Okay, I'm going to present satellite technologies today. So we have only, I think, 50 minutes, right? 50 minutes. Hocam 50 dakikamız var değil mi? 50 minutes, okay. Definition of satellite. What is satellite? So we mentioned about artificial satellite, but in general, what is satellite? Satellite is an object intentionally placed into orbit in outer space, or orbits or revolves around another object. For example, Moon, or Io, Titan, the Saturn satellites, for example. There are 82 or something, 80-something satellites revolving around Saturn or Jupiter. So, but this is the natural satellite. For example, Moon is a satellite of Earth, but we will examine human-made satellites, artificial satellites today. What is satellite in our terms is a radio frequency repeater. It's just a router. It receives signal from us, from ground station, and then distribute it or broadcast it to Earth, back to Earth. That's it. It's a satellite. But it's revolving around Earth or Moon or other objects. So we can classify satellites into two groups. The natural satellites, as I mentioned, Moon, Io, Titan, etc., or human-made or artificial satellites. These can be classified into two groups again, based on orbiting the Earth. Geostationary satellites, I will mention about them. Geostationary satellites, medium Earth orbit, MEO satellites, or LEO, low Earth orbit satellites, or highly elliptical orbiting satellites, and polar satellites. These are all classification of orbits, in fact. The other classification is based on application. Remote sensing satellite, observation satellites, for example. We use them for remote sensing. Meteorological satellites for weather predicting, for forecasting. Communication satellites, those are far away from us, 36,000 kilometers away from Earth. Those are communication satellites. Geosynchronous or geostationary satellite, we call them. Navigation satellites, GPS, GLONASS, or other systems, and scientific and military satellites. Each satellite has a mission, has its own mission, and for communication satellites, for example, used for TV and radio broadcasting, usually. But observation satellites take the photo, the Earth photos, and we, the images. We take the images, and then we try to understand what's going on. Is there any for example, mine, or is there any, for example, disaster? So we observe the Earth, and then we try to understand the Earth from observation satellites. And we have also some scientific satellites to predict the earthquake, for example. Is it possible from satellites? They are trying to understand, the scientists, but it is difficult. Satellite advantage, mobile wireless communication independent of location. For example, Indonesia, they have launched their own satellite in 1966. Dispersed 7,000 islands. Either you will connect them by cable, or just you will place a satellite into orbit and then communicate between those islands. It's going to be easy for satellites. Wide area coverage, country, continent, or globe. You can cover the whole the Earth only using 3 satellites, 3 geostationary satellites. Wide bandwidth available throughout, independence from terrestrial infrastructure, rapid install. Did you hear about Iridium satellites, for example? In 1999, during the earthquake in Istanbul, so we have used Iridium satellites because it's independent of infrastructure. If something happens here, so you can use satellites, only one mobile terminal, you can communicate with each other. Rapid installation of ground networks, low cost per edge site, for example, for Africa, or For rural areas, you can use satellite networks. Uniform service characteristics, Walmart satellite network, for example, total service from a single provider. We usually, this is TV receive only, the satellite dish antennas you see on the roof or on balcony, for example, you see some satellite dish antennas. Those are TV receive only. We have a satellite, we just receive TV signal or radio signal from here. This is one way. There is no two-way communication here. We don't transmit anything here. We just receive and we watch the TV here in the home, at home. So other networks, we have fixed earth stations, terrestrial network, the telephone, fax, or computer, or the ships can use the cars using GPS signal or portable earth station. The military personnel are using these terminals, for example. But don't forget that the capacity of fiber communication is much greater than the satellite communication capacity. This is almost 1,000. Satellite is a complementary services. They can only provide you complementary services, not the whole communication infrastructure. We only have only 1,000 capacity. Applications in communication, media, TV, disaster monitoring, mapping, weather forecasting, and security and science. We use satellites for these applications. Now, for example, Elon Musk, they have launched what was Starlink satellites. It's for internet, right? Internet connection. Communication, you already know that. The signal is traveling 310 to the 8 meter per second. It's the speed of light. So if you communicate with a man on the moon, for example, it's going to take 1 second, 1.2 seconds. But on Mars, it's going to take at least 20 minutes. So, but on Earth, it's easy. You are in America, or other guy in Turkey, it's going to take less than 1 second. It's okay. It is reasonable. Disaster monitoring, this is tsunami in Japan in 2011. There was an earthquake. It's a huge earthquake, For disaster monitoring, you can't use drones. It is difficult using drones because, everywhere is flooded. So as you see, this is Sendai Airport. This is Sendai city, so it is flooded as you see. These pictures are from satellites. As you see, it was and also Mexico, Gulf of Mexico, I think. This is oil leakage, oil accident. Also volcanic eruption, Elyaf Yallayakul, I don't know how to pronounce it, but it's a very difficult volcanic eruption. It happened in 2010, as you remember. I was in Chicago. Due to this volcanic eruption, we couldn't come to Istanbul because the planes were using another route to reach their destination. You can use drones for this type of disaster, for example, because the ashes are reaching to more than that height. I mean, the planes are 10 kilometers, 10,000 meters, or 11,000 meters. But these ashes are going to, I think, 15,000 meters altitude. Mapping, we are using satellites for mapping. And also, we are trying to understand what is there. What is the crops, the wheat or other crops. So we can define, we can calculate the plants, in fact. Mapping, just weather forecasting, this is also possible. So this is, for example, hurricane, the epicenter of the hurricane is here, as you see. These are possible from satellites, not drones. For security, we also use for security. For example, our Bayraktar TV, the Baykar drones, they are using satellites because the operation is going on on the border of Syria, but they are controlling the operation in Ankara using satellite technology. They are not on the border. But they have some other stations, ground stations there, but they are organizing, orchestrating the teams, and just they are pushing the button in Ankara. Image resolution for satellites. I'm going to give you an example here. For example, this is 1 bit information. You don't see anything. The resolution is 128 meters. So we are trying to increase this resolution each time by half. I'm going to divide by half. 64 meters, 32, 16, 8, 4 meters. As you see, there are some details are coming up. 2 meters, 1 meter, and 0.5 meters. As you see, there are many details. In satellite technology, America has 0.3 meters now resolution. In the world, France, Japan, and other countries, only a few countries can build observation satellites with that resolution, 0.5 meters. In Turkey, for example, we are building a satellite with 1 meter resolution. 1 meter resolution means, or 0.5 meter resolution means, bigger mirror, 1 meter in diameter. And also the surface of the mirror will be very smooth, only 1 micron error, RMS error. So you have to have that kind of technology or infrastructure here to build that mirror. So we paid for Carl Zeiss. You know, Carl Zeiss is a company in Germany. We paid 2 million euros for 50 centimeter mirror. 2 million euros. It's a mirror, but you can't understand. It's a very nice mirror because it is space qualified. There is a material, zero-dur material. In space, the temperature is about minus 270 degrees Celsius temperature. But if you see the sun, if your satellite look at the sun, it's going to heat up to 150 Celsius, almost 400 degree change in 1 minute. So your material should not change. Usually zero-dur only change less than 1 micron with that temperature change. So the chemistry, physics, and other basic sciences are so important. You have to develop your own material. You cannot buy this mirror if they don't sell you, or they are going to issue you have to take export license for this kind of material. You cannot do that. So basic sciences or the material sciences are so important, but the technology is also important. We have to do it together. We are going to develop technology with basic sciences. We have to study on basic sciences. So 0.5 meter is something like that. We are now working on a satellite image with resolution 1 meter. Next time, probably we will try 0.5. Types of satellite services. I'm going to just skip this part. We have some frequencies. Do you guys are electrical engineers or mechanical engineers? What social sciences? Any engineer here? Engineers are here? Oh, okay. Okay, basic science. Okay, good. You know what frequency is then? Huh? Frequency, we are changing the voltage up and down. So what's happening? With DC, you can't create electromagnetic waves with DC voltage or DC current. But if you change the current back and forth, it means AC, alternating current. So it's going to create electromagnetic field in space, electromagnetic wave. We are using these frequencies between 1 and 2 gigahertz, for example, L band, we call it L. These are GPS signals. The GPS is American. In fact, the name is GNSS, global navigation satellite systems. But GPS, the name of the America's GNSS, GLONASS is Russians, Baidu is Chinese, and other augmented systems, GPS systems. There are only 3 independent GPS systems, or GNSS systems. GPS, GLONASS, and Baidu. We are using all these frequencies, and these should be regulated in the world. Who's regulating the frequencies in Turkey? Do you have an idea here? Do you know these institutions, or TRT? It is like BBC. Excuse me? Yeah, TRT is the BBC of Turkey, let's say. RTÜK is the regulating body of Radio Televizyon Üst Kurulu, the higher council of radio television. BTK, Bilişim, neydi? Bilişim Teknolojileri ve İletişim Kurumu. BİTİK diyeceklerdi, BİTİK diyemediler biliyorsun. Bir de İletişim Kurumu var. Communication. BTK is regulating the frequencies in Turkey. FCC, you know, FCC in America is regulating those frequencies. How about in the world? Who's regulating the frequencies in the world? BM, United Nations. United Nations was established in 1945. But who's regulating the frequencies? Before that, we had some frequencies for telegraph and other technologies, right? So who is that? Do you know? Do you have an idea? ITU, International Telecommunication Union. It's established in 1866, about 90 years before United Nations. They are in Geneva in Turkey, Genoa, so Switzerland, and they are regulating the frequencies. Okay, what is regulated here? Choice of radiating frequency. You can't use any frequency. You have to organize. You have to agree with other countries. I'm going to use this frequency. You are going to use this frequency. Otherwise, it's going to be interference. You can't communicate. So other thing is maximum allowable radiated power. For example, you have a pole here. You have a radio station. You can't pump any energy here. So there is a limit. So otherwise, the other countries, for example, in Greece or Bulgaria, for example, will receive your signal, and then they will listen to your, or it's going to be interference. So there's a regulation on power, and also orbital locations, orbital slots for geosynchronous orbit, so for satellites. The idea comes from Arthur Clarke. He published an article in Wireless World. Wireless World is the magazine published in that year in England. In 1945, he mentioned that he calculated that this is Earth if we launch 3 satellites here to this distance. He calculated that distance, about 36,000 kilometers. And then he says that the angular velocity of Earth will be equal to angular velocity of this satellite with that distance. It's easy. For example, the sun is 150 million kilometers away from us, right? We can consider that the center of the universe is Earth. I can consider that way. So how long does it take to revolve around me for sun? 365 days, right? 1 year, 365 days. How about moon? Moon is closer than our sun, about 384,000 kilometers. It's less than 1 million kilometers. And it takes 29 days. So I can calculate one distance, 365, 29 days, 1 day. What is that distance? He calculated that distance, 36,000. Exactly 35,786 kilometers. So if you place any satellite in that orbit, it's going to take only 1 day to circle around that orbit. 1 day means the Earth is also revolving in 1 day. So we are going to see the satellite stationary. In fact, it's moving with 3 kilometers per second, but it seems that it's stationary to us. Relative, excuse me? Yeah, exactly. So this is for geostationary satellites. For LEO, closer satellites, for example, we have satellites 600 kilometers, 700, those satellites are moving with 7 or 8 kilometers per second. It's much faster than those satellites. But he also envisioned the use of staffed space stations in geo-orbit. There is no man went there, staffed space stations. It's not possible yet. The invention of transistor, solar cell, and traveling wave tube amplifiers in 1940s and 50s allowed relatively compact, highly reliable repeaters to be built. So transistor, solar cell, tube amplifiers are just emerging. It's, in fact, launch vehicles of the power required became available in the mid-1960s. The question is then, I have seen Saturn V in Houston, in Johnson Space Center. It's a very huge structure. There is no simulation software at that time. The computers are very low capacity. So how can they build that kind of rocket? It's a very huge rocket. The question is, moon landing, did they really go to the moon with that technology? They're asking. I believe that they went. Starting from 1969 up to 72, 12 astronauts landed on the moon, set foot on the moon. Well, I don't know. Their claims is the moon landings were faked, Apollo 11 didn't happen, humans never set foot on the moon. These are their claims, you know. You can see many videos on YouTube regarding this conspiracy. The difficulty was rockets. Suitable launch vehicles developed in the mid-1960s. So it is really difficult, you know, because if you would like to escape from, you know, there is an escape velocity for Earth. It is 11 kilometers per second. You have to have a very powerful rocket. Otherwise, you know, the first satellite is 1957. Russians built Sputnik 1 satellite, and they placed that satellite in the orbit in 1957, 4th of October 1957. It was the space age started. Before that, we just observed. In 1609, Galileo built a telescope, and he, you know, found some 4 satellites of Saturn. No, Jupiter. I'm sorry, Jupiter. Those are Galilean satellites, we call them. And then telescopes were used at that time, but still using. We have space telescopes, for example. But at the first time in history, in 1957, they placed a satellite into orbit, artificial human satellite into orbit. It was a huge event. The Sputnik 1, as you see, United Soviet Socialist Republic, right? In 1957. This satellite was active for 21 days, no communication capability, only beep signal. We received only beep signal. Why it is for 21 days? Because it has a battery died. It died. So we lost this satellite after 21 days. After 3 months, I think it burned into the atmosphere. And Explorer 1, these are USA works, USA, as you see USSR, here one more. And if you compare the satellite technology, by far, America is the first, by far. If you, for example, if you sum up all the budgets of other countries, America will be the first, by far. because Roscosmos only spent $2 or $3 billion. ESA, European Space Agency, other countries, if you add them up, you cannot reach the budget of America. Syncom is the first geosatellite in 1963. The Intelsat, VSTAR, and other satellite projects are coming. In Turkey, the first time after 37 years, in 1994, Turksat 1A was launched, but it was a failure, launch failure. So in that year, in 1994 again, in October, 1B, Turksat 1B satellite was launched in Kourou, French Guiana, in Kourou, South America. What is geostationary satellite? This is the exact value of period. It is away from us, from the equator plane, in the equator plane, and it's going to take only 1 day. Its period is 1 day. But for LEO satellites, only 90 minutes, 90 or 100 minutes, roughly. So it's going to revolve 14 times, 16 times. For example, ISS, International Space Station, is revolving 16.5 times a day. Medium Earth orbit satellites is usually away from us up to 15,000 kilometers, I think. For example, GPS satellites are using that kind of orbits. Highly elliptical orbit, Russians use this kind of orbit, is about 20,000 kilometers. Period is more than 12 hours. It's something like that. The Earth is here, LEO is very close. Observation satellites are very close because we're going to take picture. If you would like to take picture, you can't get away from the object, right? You have to be close. So these are LEO, low Earth orbit satellites. We have one inner Van Allen radiation belt here. We have, I think now, 3 Van Allen radiation belts. They determined the third one a few years ago. And we have medium Earth orbit satellites here, and geostationary satellite, 36,000 kilometers. It is something like this. Earth is scaled, the distance is scaled, this size is not scaled. The moon is 10 times about this distance, more than 10 times. So you can't draw Earth, moon, and it is this distance between them. You can't. It is difficult for A4 size paper. How do artificial satellites stay in orbit? This is north. We are using our right-hand rule, right? How is the Earth is rotating? From east to west or west to east? Don't memorize this way. Earth is rotating using right-hand rule. I don't care about west or east. This way, that's it. This is north, this way. It is rotating this way, that's it. Okay? Because probably in Turkey, I know in Turkey they're teaching this concept, east, west, west, east. So you can confuse it. But right-hand rule, it's simple, right? This is, if the Earth is something like this, so it's going to rotate this way. That's it. Simple. Okay, if we have an object here, the mass is m satellite. This is the velocity it gained. This is centrifugal force. So, I'm sorry, gravitational force. This is centrifugal force. If you equate these two forces, this is going to cancel out, right? M will cancel out. So if you place a 1 kilogram object or 10 tons object, it doesn't matter. If you place it, it's going to be there and independent of its mass. So it's going to be, this velocity is important. If you keep this velocity, for example, it is away from us about 700 kilometers. Our satellites, RASAT, for example, is something like that. So it's going to burn up in the atmosphere maybe 300 years later. Because this velocity is constant. If there is the air molecules here, that velocity will be lessened day by day, and it's going to burn up in the atmosphere. So you have to keep this velocity. For example, for ISS, International Space Station, they boost the system for 15 days. You know, one in a 15 day. For example, they have to keep their distance from Earth. It's about 350 kilometers. Sometimes it's about 400 kilometers. So they have to keep it because it's lessened day by day. There are many geosatellites, about 600 geosatellites. These are our, let's say, longitudes. The countries that are geographically spread have used regional satellite systems. Indonesia, I mentioned about this. Canada, USSR, the Russia. Canada was the first country to build a national telecom system in 1974. I was born in that year. So, new skies, so available spectrum in frequency in C-band was occupied fully by 1985. For example, in Turkey, we don't have C-band. We can't use it. We are using KU band and KA band. Because we were late, the countries shared that frequency, and then they owned that frequency by 1985. Because our first satellite was launched in 1994, about 10 years later. Now we are using KU band. Okay. There are some international organizations, you may heard them, Intelsat, Eutelsat, Inmarsat. They hold some conferences. Turksat satellites, we have Turksat 1B is in graveyard orbit, 1C, 2A. We have 3A active satellite, 4A and 4B. Even we have now 5A and 5B satellites. Mitsubishi, Airbus built those satellites. What happened to Turksat 1A? It was launch failure, because I didn't list it here. It was launch failure. What is the naming convention? 1A, 2A, 3A. For example, you build a car, Toyota, for example, Toyota, I don't know the names, the models, Toyota something. If you build the same car, it's going to be 1B. The same car, 1C, something like that. So, but if you change the model, it's going to be 2 or 3. This is the naming convention of satellites in Turkey. We have some orbital rights, 31 degree east longitude, 42 degree and 50 degree east longitudes. You know what longitude and latitudes, right? The 0 is here. This is Greenwich, going from England, right, London. This is 0, prime meridian, or longitude. And 36, we have in total 360 longitudes. And starting from equator, we have 90 latitudes, north latitudes, and 90 south latitudes. So 42 degree means almost, because in Turkey, where is Turkey? For example, this is 0. Turkey is between 26, 45. Almost here. These are the longitudes and latitudes of a country, right? We have 36, 42 latitudes, 26 almost here, and 45. So our satellite will be 42 degree, for example, starting. So you get away from this point, 36,000 kilometers from equator. These are satellites. If we consume all the fuels in satellite, because we are using that chemical to control our satellite. Otherwise, the satellite will hit other satellites maybe. So you have to control from ground station. If we come to an end for satellite, if you used up all the fuels, you have to get rid of this satellite. This is graveyard orbit. This distance is about 36,000 kilometers. You have to add 150 kilometers more. And we place another satellite in that orbit. If you keep it empty, the ITU will get that orbital rights again from you. So we have to keep satellite there. These are coverage areas for any satellite, in fact. Turkey coverage, east coverage, west coverage. But you know, Earth is not flat. Do you believe that it's flat? Is there anybody believing Earth is flat? Okay, good then. I don't know, because usually the finance guys or other social, sciences guys are believing the Earth is flat. So any astronomer or any physicist or engineers cannot believe that, right? Because we are doing some calculations. We are going to face some errors. If the model is wrong, right, you will end up with something wrong. But we don't see any wrong. So Earth is not flat. So we take some pictures, by the way. So I know that it's not flat. Launching and placing into orbit. I just skipped this part. Okay. The satellite is here. From the center, it's about 42,000 kilometers. We keep them into this window. The speed is 3.1 kilometer per second. Per second, this is important. This is equator plane. And in this window, it's about 75 kilometers by 75 kilometers. In this window, we can operate 9 satellites, up to 9 satellites. It's going to be difficult. For each day, maybe for 2 days, for each 2 days, we have to control our satellites, not to hit each other, because they can collide. For forces acting on a satellite, the satellites are not stable because we are placing into orbit, but there are some forces affecting these satellites. For example, Earth gravity is one of them. Lunar gravity, because these are celestial bodies. It's, attracting these satellites, and solar gravity, also solar radiation pressure, thermal forcing, and planetary radiation pressure and atmospheric drag. If it is in the atmosphere, it's closed atmosphere, there's an atmospheric drag, it's a very important effect. And also antenna thrust, and also tidal effects due to this lunar, due to this moon existence, right? We have some tidals, day and night. So these are affecting our satellite position, and we are correcting them. Also, we have some planetary gravity, general relativistic effects. Jupiter or Saturn, for example, is also has an effect on our satellites. Okay. Our disturbing effects are major ones: Sun, Earth, and Moon. For example, the Sun and the Moon is on the same side. It's going to attract more. Then your satellite will gain this inclination angle. So we have to keep our satellite in this color. Is it blue? I don't know. I am colorblind. So what's that? Is it blue? Okay. So this is equator plane. So we make north maneuvers to correct it, to correct this inclination angle. And also, Earth is, as you know, it's not perfect sphere. It's 21 kilometer less the diameter in the polar axis. And also the south hemisphere is heavier than the north hemisphere. I don't know why. Also from the north, from the top, it's kind of potato. These are exaggerated drawings. So these are affecting our satellite's orbit and in the equatorial plane. And also, if you, for example, if you keep your satellite here, this is our satellite. If you don't do anything, it's going to drift to this position. If you have any satellite here, it's going to drift to this position. There are 2 stable points in the orbit, so we have to correct it. Energy issue, for some time, equinoxes, for example, vernal or autumnal equinoxes, the satellite will not see our sun. It's not going to generate enough electricity, so we have to use our batteries at that time. Satellites have 2 parts, payload and bus configuration. Payload means that is the part of the satellite we generate revenue, we make money. That, for example, for a pregnant woman, what is the payload? The baby. Baby in the womb is the payload. Every other functions work for that payload. Because you understand payload now. This payload is communication system, antenna and repeaters. Other systems, structure, AOCS, propulsion system, electrical subsystem, thermal, computer, everything that is working for payload because we generate revenue from payload. Payload is important. For example, for a car, payload is the man, right? We have a HVAC system, we have other systems where we have steering wheel, so payload is the man. We have that's why do we design a car to travel or to carry something, to carry man, right? So payload is the man in that case. We have antennas, and we have propulsion system, fuel, monomethyl hydrazine and nitrogen tetroxide. We have an apogee motor here and thrusters here. We use for orbital corrections. And we have also star tracker, gyro, core, sun sensor, reaction wheels. You know, with the reaction wheel, what can we do? You are on Earth, you can turn anywhere. It is easy. But how about in space? You don't touch anything. How can you do that? You're going to turn. How can you do that? If you go from one point to other point, use thrusters and apogee motor. Use fuel. M1 times V1 is equal to M2 times V2. The moments will be equal, right? Then you can go from one point to other point. How about rotating? For example, I'm going to face you, but now I'm going to other celestial object, for example. How can you do that? Using reaction wheel. Because reaction wheel, tepki tekeri, will generate a moment, right? We have 3 reaction wheels, active and 1 redundant. So if you write the algorithm, so you are going to, for example, the rotating wheel, for example. Did you hold it? Did you do that experiment? Rotating wheel will generate a moment, so you will change its direction then. We have thermal control subsystems, thermal pipe, isolations, the multi-layer isolation, dye coating, active and passive thermal control equipments. How many minutes left? Okay then. We have many satellites, pico, nano, micro, mini satellites. These are 1 kilogram, less than 1 kilogram, less than 10 kilograms, 100 kilograms, and 500 kilograms. The others are the regular satellites. Boeing, Lockheed Martin, Lola Systems, Orbital, these are the manufacturers, commercial manufacturers in America. We don't mention about NASA here, for example. Astrum, Thales Alenia Space in France. And other countries can make their own satellites. Turkey is also here. I think that's enough. If you have any question, this is Turksat 3A. I'm here in France, in La Boca, Cannes. Excuse me? In La Boca, Cannes. You know Cannes? Film festivalinin yapıldığı yer. Cannes. Côte d'Azur. Côte d'Azur. I was there. Maybe I can answer your questions if you have. There are many. You know, in 45 minutes, it is nothing to mention about these satellites, satellite technology. It's nothing. Because we give lectures during the whole term. I can only mention about introduction. Cannot, you know, go into the details of the calculating any link budget, mass budget, or other design techniques. You cannot do that. In 45 minutes, you just heard it. Okay, there are some satellite technologies. We are using them. They are important, but their capacity is not so much. compared to fiber. Just know these information. That's enough.